Hello and welcome to online lecture number 17 for Chemistry 112 during the spring semester of 2020. In this lesson, we'll finish chapter 17 with the topic of electrolysis. So electrolysis is important because the spontaneous reaction, the reaction happens on its own. So for example, the reduction of copper by zinc may or may not be the actual reaction we want. We may want the reverse to occur. We may want copper to reduce zinc. But this is a non-spontaneous reaction as indicated by its negative standard cell potential. Doesn't mean the process won't occur, just because it's non-spontaneous, it's not going to occur without ongoing outside intervention. So electrolysis then is a process in which we use electrical energy to drive a non-spontaneous reaction to occur. This is in contrast to what we saw with galvanic cells. In galvanic cells, a spontaneous reaction occurs, so essentially chemical energy is used to create electrical energy. Here, we're going to use electrical energy, an outside source electrical energy, to create chemical energy. The magnitude of the negative standard cell potential, it's negative because it's a non-spontaneous process, and that number, the magnitude, that magnitude represents the minimum potential, minimum voltage necessary for electrolysis. And so our electrolysis setup, they look like this, where we have some sort of non-spontaneous process we want to occur. We connect a battery. The battery will provide enough potential greater than what we expect from the standard cell potential, and then connect it such that on the anode and on the cathode, the cations are reduced at the cathode. So reduction still occurs at the cathode as it does in a galvanic cell, and oxidation still occurs at the anode as it does in a galvanic cell. And a very important difference, though, is in a galvanic cell, the anode has a negative potential to it, whereas in the electrolytic cell, it has a positive potential. The anions are attracted to the positive potential of the anode where they are oxidized. And then at the cathode, which normally would have a positive potential in a galvanic cell, in an electrolytic cell, it has a negative potential. So the cations are attracted to the negatively charged cathode where they are reduced. So we'll take a look at a couple examples of electrolysis and then get into a little bit more quantitative aspects of electrolysis. So first, electrolysis of water, very important electrolytic reaction. Where water can be split into two elements, oxygen and hydrogen. And this is a non-spontaneous process because it has a standard cell potential of negative 2.06 volts. But if we apply more than 2.06 volts externally, then we can force this reaction to occur. At the anodes where oxidation will occur, so water will be oxidized to oxygen and hydrogen ions with the production of electrons, which all oxidation processes involve. And then the cathode half reaction is a reduction where the hydrogen is reduced from water to hydrogen gas with also production of hydroxide ions. So this might be kind of a typical setup. We'll connect to a battery that provides enough greater potential than 2.06 volts. A 9-volt battery, for example, will work for this, will suffice for this process. And then the cathode and anode connected. At the anode is where we expect to produce oxygen gas. At the cathode is where we expect to produce hydrogen gas. And so if we're able to collect the amount of gas present, we find that as based upon the stoichiometry, we produce twice as much hydrogen gas as we have oxygen gas. So our balloon on the hydrogen side will fill up twice as fast, get twice as large compared to the oxygen side. And finally, end up with some quantitative electrolysis examples. It's based upon Faraday's law. Faraday's law says the amount of a substance that is consumed or produced at an electrode, an electrolytic cell, so where electrolysis is occurring, is proportional to the amount of electricity that passes through the cell. In other words, if we're able to keep track of not the energy of the electrons has to be sufficient enough to cause a non-spontaneous process to occur. The potential has to be greater than the negative cell potential of that non-spontaneous process, but rather the current, which is a measure of the rate of the electron flow. So if we're able to keep track of how many electrons have passed via this battery or other external source. Then from that, we're able to determine how much a particular substance has been reduced or otherwise be able to quantitatively describe an electrolytic reaction. So with current, as we introduced a couple of lessons ago, current, we used amperes or amps to describe current. And 1 amp is equal to 1 coulomb per second. In electricity, charge, coulomb, is carried by the electrons. So as a result, then, current is one way to keep track of how many electrons have passed through the cell in a given unit of time. And because current is this ratio of charge, coulombs, and time seconds, current can be used as a conversion factor to relate charge and time. So the charge, so I abbreviate it as a capital Q, is equal to the current times time, as long as the units are what they should be. But then where does that charge come from? Well, the charge also comes from the number of moles of electrons. So number of moles of electrons, N times Faraday's constant, also gives us the charge. So because we can define charge or calculate charge either with this equation or this equation, because the left side of the equation is the same, that must mean that the right side of the equation is the same. And then we'll take advantage of that as we go through a couple examples of calculating how much of a particular metal ion can be plated onto another substance or some other quantitative aspects of electrolytic cells. Our first example is interested in how many moles of oxygen will be produced by the splitting of water for 1.5 hours at a current of 3.00 amps. So we have our question of how many moles of oxygen do we expect to produce from a splitting reaction in which we've conducted a current of 3.00 amps over a time of 1.5 hours. And this is our overall redox reaction. What we're interested in, though, specifically is the oxidation half reaction, where the oxygen is being oxidized from its oxidation state of -2 in water to an oxidation state or number of 0 as part of oxygen gas. So notice of this half reaction, the most important part is that for every 1 mole of oxygen is produced, it requires 4 electrons. So there's a 4-to-1 ratio between the number of moles of electrons produced and the number of moles of oxygen produced. So to keep that in mind, we have time and we have amps. Remember, amps is just another way of expressing coulombs per second. So our strategy is to start off with time, and we'll start off with time in hours. We convert that into minutes, and then convert that into seconds. Once we have seconds, then with the current, because current is 3.00 coulombs per second, this will allow us to convert it into charge in coulombs. That's important because then, so this would be our, using our current as a conversion factor here. Our next conversion factor, because I saw that relationship in the previous slide, is we go from charge in coulombs to moles of electrons using Faraday's constant. And then once we have moles of electrons, we can go from moles of electrons to moles of oxygen, which is what the question is asking for, using the balance equation, specifically the relevant balance half reaction equation. As we saw before, for every 1 mole of oxygen is produced, it also produces 4 moles of electrons. So putting everything together, we have 1.5 hours. And we have 1 hour, of course, equals 60 minutes. 1 minute is equal to 60 seconds. Current, 3.00 amps. So this says that there are passing a current of 3.00 amps, which is equal to 3.00 coulombs per second. Gives us the total charge that's passed through our electrolytic cell. Faraday's constant allows us to convert from charge into moles of electrons. So 1 mole of electron carries 96,485 coulombs, Faraday's constant. And then from our balance equation, it's a 4-to-1 ratio. So for every 4 moles of electrons that are transferred, 1 mole of oxygen is produced. As we're stopping, because that's what the question is asking for, is moles, but certainly we could calculate grams, or if we know the temperature and the pressure, for example, we could also determine the volume of oxygen produced over this same amount of time with this particular current. So we plug in our numbers. We have 1.5 times 60 times 60 times 3.00 times 1 times 1 divided by 96,485 divided by 4 gives us our answer of 0.0420 moles of oxygen. So that's how many moles of oxygen we expect to be produced by this setup, passing a current of 3.00 amps over a time of 1.5 hours. If the question was about hydrogen, very similar setup, very similar process. The only difference that we would be interested in what's current at the cathode. So we'd have to start with a half reaction describing the creation of hydrogen from the splitting of water, the reduction of hydrogen to hydrogen gas. In our next example, we want to determine how long hours will it take to electroplate 10 grams of silver onto a spoon from a solution of silver nitrate with a current of 4.80 amps. So notice our setup. The cathode has the negative potential. So electrons are pouring into the cathode where reduction is going to occur onto the spoon to the electroplate to reduce silver ions to silver metal on the spoon. And then the other silver electrode is serving as the anode. So we'll determine how long it's going to take to put additional 10 grams of silver onto this particular spoon. So this is our setup. And determine how long it's going to take at this current to put 10 grams of silver. In other words, for this half reaction to stoichiometrically produce 10 grams. Notice that with these half reactions we saw in the previous example, one of the key relationships is the relationship, the mole-to-mole relationship between moles of electrons and moles of what we're interested in doing with this electrolytic cell. So specifically, we want to produce 10 grams of silver, that's equal to so many moles of silver, and according to this half reaction, for every 1 mole of electrons that pass, we're able to produce 1 mole of silver. So that's another important conversion factor relationship we'll use to ultimately answer our question. So we want to start though with the mass of silver that we want to produce. And just like in chemistry 1, if you're giving grams of substance, usually the first step, and usually the first correct step, is convert that to moles. So we'll do that, of course, with the molar mass conversion factor. Once we have moles of silver, now we can use our balance equation, our balance half reaction equation in the case, to relate moles of silver to moles of electrons. Once we have moles of electrons, we want to convert that into coulombs, into total charge. And like we saw in reverse in the previous example, we can do that with Faraday's constant. And then once we have coulombs, we have current. So with coulombs and current, we can then determine time in seconds as our conversion factor. And once we have time in seconds, it's trivial enough to convert to minutes, and finally 2 hours. So it's several steps in this process, but for the most part, we've seen these steps before in maybe a different context. The only new steps perhaps are using Faraday's constant to convert from moles of electrons to charge, and then using the current to convert from charge into time. So we start off with 10 grams of silver. Convert to the moles using the molar mass information. So we have 1 mole of elemental silver has a mass of 107.9 grams. According to our balanced half reaction equation, for every 1 mole of silver produced, it consumes 1 mole of electrons. So it's a 1-to-1 ratio between the moles of silver and the moles of electrons. Faraday's constant allows us to convert from mole electrons to charge. So 1 mole of electrons equals 96,485 coulombs. With the current, then that allows us to convert from coulombs to time. So we have a current of 4.80 amps, which is 4.80 coulombs per second. 4.80 coulombs for every 1 second. And then finally, seconds to minutes and minutes to hours. We have, of course, 60 seconds in a minute and 60 minutes in an hour. So we put in our numbers. Notice all the units are canceled except for time and hours. 10 times 1 times 1 times 96,485 times 1 times 1 times 1 divided by 107.9 divided by 1 divided by 1 divided by 4.8 divided by 60 gives us our answer as 0.517 hours. So a little over 30 minutes or so. That's how long it would take to electroplate 10 grams of silver at this current. Obviously, if we were able to increase the current, practically that would increase this number here in the denominator, which would then, as expected, decrease this time. So it would take less time at a higher current, more time at a lower current to electroplate the same amount of silver. So with this, we finally finished chapter 17, and our last couple of lessons will end the semester with our introduction to nuclear chemistry.